year ago, I started a new job for a startup that builds software for legal teams. Prior, I had no idea what eDiscovery was and had never heard of Temporal. Today, I'm going to be talking about both of those things. My name is Elena Gray. I'm a senior software engineer at Logical. Logical is a market-leading eDiscovery platform that's built for the masses. Our goal is to accelerate the democratization of discovery. I graduated from the Rochester Institute of Technology with a degree in IT and have spent the last 7 years working in the tech industry. Born and raised on the East Coast, but recently moved to Nevada with my partner and our dog. Before I dive into a few temporal use cases, which I know is why you all are here today, I am going to take just some time to talk about eDiscovery, what it is, as well as some of the challenges and opportunities that it provides. Discovery is the process of obtaining and exchanging evidence or information that may potentially become evidence in litigation. As our world has moved almost entirely to electronic communications, the term eDiscovery is now used for when electronic records are involved. Those electronic records are referred to as ESI, which is short for electronically stored information. eDiscovery, much like a temporal workflow, is simply the process that is followed by legal teams pre-trial. As depicted in the slide, these are the steps or activities that make up that workflow. The output of the workflow is then the eDiscovery findings that will be shared with all parties involved in the lawsuit. The variety of ESI is continuously evolving. We all leave a daily trail of electronic evidence that can often be used to track our every moves. So it should be no surprise that digital evidence is playing an increasingly important role in legal cases. In order to explain the eDiscovery workflow in a bit more depth, I'm going to use the notorious case of Harry Potter versus Mr. Filch. So this case unfolded at Hogwarts, the School of Witchcraft and Wizardry, where a student, Harry Potter, has filed a case against the caretaker, Mr. Filch, alleging that he misused a magical artifact, the Marauder's Map, to illegally track students' whereabouts. The first thing that will happen is attorneys will identify individuals or parties that may have had access to the map or exchanged any information related to its use. The scope of data to collect will be any of the digital communications or metadata related to those individuals. To ensure the integrity of the data, the attorneys will ensure that any of the discoverable information cannot be modified or deleted. In fact, when such information is modified or deleted in a non-routine manner, that can be considered spoliation, which is a sanctionable offense in many cases. Next, our ESI will be gathered from various sources. We'll want to collect data from the Hogwarts email server. They use Gmail. This will include an archive of emails, including any that may have been deleted. We'll also want to collect data from any digital communication platforms. Surprisingly, they also use Microsoft Teams. And we'll also collect data from any personal devices, such as laptops and cell phones. You can imagine this is Harry's legal team right now. They're probably feeling quite overwhelmed. This is a lot of data to collect and review. On top of that, the US specifically has a long tradition of broad discovery, which allows litigants to request a wider range of information and document types than many other countries. What used to be hundreds of boxes that would be hand-reviewed and delivered between parties is now millions of electronic records of various types, each additional document type adding its own complexity to our workflow. During processing, we will filter and organize our data to remove any duplicates or irrelevant information. At this stage, we might want to group all emails either sent to or by Harry or Mr. Filch. And in doing so, it's likely that we'll come across a few duplicate email chains, so we'll want to remove those so that we don't do extra work during review. Without a tool like Logical, this process can be extremely time-consuming and error prone. We're humans, we're bound to make mistakes. At Logical, we found that up to 97% of data ends up being non-responsive noise. That means we're collecting a lot of data for a relatively small amount that will actually be relevant. On top of that, this process is really expensive. Legal teams, 80% of litigation teams are spending 7 figures or more on eDiscovery. And as you can imagine, this is just one step in the entire legal process. Processing is also a step when we're going to convert our data into a format that's more suitable for review and analysis. Often that format is an image, such as a PNG. During review, attorneys will assess the collected ESI for relevance, confidentiality, and privilege. Let's say we've pulled a phone conversation between Mr. Filch and his doctor. That will be considered privileged and should not be disclosed. Much like unraveling hidden messages within the Marauders Maps moving ink, during analysis, legal teams will try to identify patterns, trends, or anomalies in our data. Often this will involve using complex technologies, such as complex searches, predictive coding, and data analytics. The use of such tooling really increases the accuracy of finding relevant documents, as well as that chance of finding the smoking gun. Finally, production is when our relevant and selected ESI will be delivered to opposing parties in a format that's suitable for legal proceedings. Mr. Filch's team may have requested a responsible deadline, so Harry's team is going to be under pressure to adhere to that, and this is just another reason why they really need to use some eDiscovery tooling and software. So I've taken the time to kind of give a high-level overview of eDiscovery, as well as try to point out some of the challenges and many opportunities of using tooling such as Logical. I now want to shift gears and talk through what that looks like for us at Logical, as well as dive into some of the temporal use cases. So the logical processing pipeline is a workflow that we use internally when ESI is uploaded into our system. As you see here in the slide, these are the steps that each document will go through. Depending on document type, there may be different steps that we run, but these are kind of the high-level happy path of what will happen. So we'll run virus scan, do some file type detection, extraction and explosion, metadata, where we'll try to pull out metadata about the document, as well as generate some of our own. Rendering, which is when we convert that document to an image. And then OCR, or optical character recognition, when we try to extract text from the image. So to put this into kind of a rough architecture diagram here, this blue box is a single deployable. All of our workflow code lives in our core processing service, which is a Ruby monolith. For each of the steps or activities you might think of, we're using background async jobs. For this, we're using rescue and sidekick. While rescue and sidekick are great, and they do give us some visibility, we don't have a good big picture of where a document is in our workflow. We may know what queues are running, how many queues are processing jobs, but again, we don't have that high-level view that we're really looking for. We also don't have good insight into retry counts or what any certain stage is configured with in terms of timeouts and things of that nature. On top of that, there's many other problems that we have in working with our Ruby monolith, as I'm sure that many of you here have experienced yourself. Our code base is tightly coupled. It's also grown quite large. This in turn has slowed down our CI/CD pipelines, and we don't really have the ability to scale certain pieces of it in a way that we'd like to. Now we have taken a few first steps towards a microservice architecture. What I didn't point out earlier here is we have this additional processing service, and that's deployed locally with our Ruby monolith and communicated with via a gRPC client. We also publish external events via both Redis and SQS, which allows to communicate to other external systems. And what I really want to kind of highlight here is kind of the sprawl of tooling and technology that we have going on, as well as the different communication mechanisms that we have. So why did we consider temporal? Well, it really boiled down to three things for us. First, we wanted to convert certain pieces of our pipeline to standalone services that we could scale independently. In doing so, we wanted a consistent way to communicate with these new microservices. Finally, we wanted a consistent tool for implementing our workflows across languages. This was really important to us. We didn't want to be locked down to any given language, and we wanted to have the ability to choose the right language for the task at hand. So the first use case where we implemented temporal workflows was through a feature request. Imagine we have this audio conversation between Mr. Filch and an anonymous caller. Well, this is quite relevant to our case and something that we'll want to include. The problem is there's some sensitive information in here, some PII. What legal teams will need to do is redact that, and so that's a feature that we wanted to provide. This is especially important during the production phase where this audio file will be exchanged with the other parties. At Logical, we did already have a feature for audio transcription. So we're using AWS Transcribe and we get a transcript like so, but we wanted to support the actual redactions themselves. So instead of continuing to add to our monolith, we came up with this new architecture that would allow us to apply audio redactions as a separate temporal workflow and service. We chose to use Node and TypeScript due to the ease of initial project setup, as well as the speed of development and deployment. On top of that, we wanted to take advantage of Temporal's first-class SDK support. For actually applying the redactions to the audio file, we're using a popular command line tool, FFmpeg. FFmpeg can be a quite expensive operation depending on the queries that we use. So we knew that we wanted the ability to scale independently. So this is what the workflow itself looks like. It's quite simple. As you see, as input, we give a path to the original audio file, which is just an S3. We also give a path for where we'd like the redacted audio file to be stored, as well as an internal kind of contract we came up with for what portions of the audio should either be silenced or removed and replaced with a beep. The gray circles are the activities of the workflow. The first thing we do is download that original audio file and store it to local storage. We then use FFmpeg to create a redacted version of that audio file. Next, it gets uploaded back to S3, and then we do some cleanup of the local file storage. Well, as you can see, all of these activities are communicating with local storage. Because of that, we need to ensure that all of these activities surrounded by the red box here are ran on the same worker. If you can imagine what might happen if we download the audio file and then a different worker picks up the task to actually create the redacted version, well, we wouldn't have the original audio file to do so. So in order to do this, we are using sticky activities, which ensures that all of our activities are listening to the same task queue and worker. Well, this works great, but we ran into a different problem here. So what happens if our worker goes down? Well, this is something we experienced, and what did happen is our workflow just hung indefinitely. Well, you might say, okay, well, you can use a workflow start to close timeout. Well, we did consider that. The problem is we have various audio files that we're dealing with. Some may take longer than others, and we don't want to wait longer than we have to. Plus, we don't want to end with our workflow in a failed state. So instead, we're using schedule to start timeout, and this allows us to detect when a worker has gone down in a relatively short time and restart our workflow on a new worker. The next use case we had at Logical was modification to an existing piece of our pipeline. So imagine we find this zip file on Mr. Filch's personal laptop. It's labeled map stuff. We probably want to take a look at that. Well, this is something that would happen during the explosion stage of our pipeline. where we'll extract the contents of the zip file. Imagine a scenario where we're dealing with zips within rars within tars. It's a very possible scenario and one that we handle during Explosion. So our current way of doing things was a divide and conquer approach. Each container type would kick off its own background job and so on. Well, this was working fine, but there was a couple problems with it. We didn't know how many files were uploaded up front, and so we couldn't tell how long we were in processing that container file. On top of that, we had many kind of complex failure scenarios in our workflow. It wasn't very possible to pick up and kind of resume in any partial failure scenario. So what we wanted to do instead was recursively explore that container file up front. And to do this, we built a new service that would create a collection, which is basically, think of like a JSON schema key value pair to represent the contents of that container file. We're using Avro schemas, which are a compact binary schema-based encoding. And that allows us to pass a single file into the rest of our pipeline, which can then kick off a workflow for each of the documents within the container file. What this buys us is a few things. It improves our customer experience. Imagine we have a progress bar. We can now accurately display how far along we are in their file. It also improves the time to first value by unlocking features that were not possible before. We may be able to present our users with the option to select which files they want to upload instead of locking them into processing the entire file. This is especially important when you're paying per gigabyte of processing, and something that we want to enable our customers to do. Finally, it speeds up that reprocessing scenario that I mentioned and removes some complexity from our existing code base. So for this workflow, again, we're passing a path to that original container file, which lives in S3. We then build that collection that I was just describing as our first activity. Next, we ingest our collection, which is creating database entities for each of the documents. And then we schedule those documents for processing, which will run through the rest of our pipeline, file type detection, virus scan, etc. Finally, we do some cleanup here. So for this workflow, we decided to use Kotlin. We chose Kotlin because it had the best native support for dealing with those file types as well as building that collection. For the rest of the activities, those are actually written in Ruby. And this was really helpful for us because we were able to reuse a lot of our database connections and kind of coupled business logic around that. In order to build the Ruby activities, we are using a third-party library, the Temporal Ruby Coinbase library. And the last thing I want to call out here, which I didn't point out earlier, but we have this fallback activity that we implemented. And the reason was, this was a modification to the core piece of our pipeline and something that was deemed quite risky. So in order to deploy it and kind of de-risk that deployment, we didn't want to block customers if something went wrong within the new code pass. So in code, it's quite simple. Try catch on certain non-recoverable workflow failures. We're using a fallback activity, which then sends that file back to the previous way of doing things. So this really helped us deploy things in a seamless manner. All right, the last use case I have for you all today was another feature request. So as I mentioned earlier, Hogwarts uses Microsoft Teams. We definitely want to pull some data from there. Microsoft Teams is also a platform that many of our customers use and something they were wanting as well. So this workflow is a lot more complex than the prior two. Don't worry, I'm not going to step through everything here. I just want to give you a high-level picture. Again, we are using Node and TypeScript for this workflow, which was great because we got to reuse a lot of the patterns from our first workflow built for audio redactions. The first workflow is essentially parsing the JSON from the Microsoft Teams API and creating database entries for the different aspects, so messages, channels, etc. It's also chunking the channel and direct chat message data into kind of groups that we could convert into files. The bottom two workflows are running in parallel for chats, which are basically direct messages, and channels respectively. And what these workflows are in charge of is taking that chunked, the groups of messages, and then converting them to rendered HTML documents. Those HTML documents are then the input documents that we send through the rest of our processing pipeline. So the first thing you'll notice, we are using child workflows here. We're dealing with a variable amount of data as we're pulling this. It could depend on the time frame selected or how active a certain organization may be within Teams. So in order to not hit event history limits, we're using continuous new, which starts a new workflow execution with a fresh event history. We're expecting, this workflow is not yet in production, it's close, but we're expecting the magnitude of millions for any given messages, regardless of channels or direct. Another thing that was cool about this workflow was we had the opportunity to reuse one of the activities from a prior workflow. So this was an activity that we're using for the file or container explosion, which handles creating the database entities for each document. We reused that Avro schema that I was talking about earlier. And because of that, we're able to pass these HTML documents into that activity, which handles kicking them off into our processing pipeline. Finally, one thing we really benefited from with this workflow was the use of open telemetry and traces. We're using Datadog for visualization of this flame graph here. Because we're dealing with multiple child workflows, it was kind of hard to visualize like what components might be taking too long or what activities were in need of optimization. So we really relied on the traces for that. So a couple key takeaways before we close here. In the past few months, these are kind of what I've boiled down to as, key notes. First, definitely join the Temporal Slack group if you haven't already. It's an amazing resource and one that we've used frequently. Also, choose the right language for your task. I think that's one of the kind of major benefits of Temporal. So lean into it and really take advantage. We've already been able to use multiple of their SDKs and quite quickly. It's been a matter of months. Keep your inputs small to avoid event limits. As you saw with all of our workflows, we were passing in an S3 URI instead of the actual raw data file. When possible, write generic activities. Definitely don't force it, but when you have complex business logic that you don't want to have to rewrite, especially across different languages, this was really helpful and something that we really sped up our development. Configure proper timeouts. So as you saw, there's different use case for certain timeouts. I know when I was first looking into Temporal, the timeouts specifically took a long time for me to wrap my head around in terms of when to use which one. So take the time to really understand them and understand which timeout you go with and what it's doing. Finally, keep it simple. Start with a small use case if you can. Don't add custom error handling or modify the retry logic unless you really need to. And that's all I have for you today.